Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be showing or proving to you the eigenfunction of a continuous time linear time invariant system, or LTI system, where we're going to prove that the output y of t of a LTI system h given an input x of t can be represented as this h of s times e to the st, where e to the st is the eigenfunction of this continuous time LTI system with a corresponding eigenvalue h of s, which is equated to the integral from negative infinity to infinity h tau e to the negative s tau d tau. And essentially, by the end of this video, you're going to understand the proof behind this statement. So before we do that, we need to take this first slide. And in general, what we say is that the impulse response h of t of a system h is defined as this h of t when my input to my system h is the Dirac function or the unit impulse function. So essentially what I'm going to say is that this h of t here is what I call my impulse response. This here is my system, and this here is my delta function, also called the unit impulse. Okay, and this system can be any system, right? It's not restricted to being an LTI system. And since this point is a fundamental to understanding the eigenfunction of a continuous time LTI system, I'm going to really dive into it to clarify the point. So what this definition is saying is that if I have a system, again, any system, call this H, and my input, let's say x of t, is equated to this delta t, then this means that my output y of t is equated to, we represent it as h of t, which is equated to my system h when the input is this delta t. And again, this is just a definition given by engineers. Let me take a quick example to really drive home the point. And for this example, imagine if I have a system h where what it does is it takes the integral from negative infinity to t of my input. So x tau d tau. So what it's saying is whatever input you put into this h, it's going to take an integral of that input. So engineers say that then if x of t is equated to delta t, okay, which is a special function, then my output y of t, which again we call h of t, is this impulse response. So what we get is h when we input x of t, or h when we input this delta t. And if we input delta t into this integral, we're going to get h of t is equated to my integral from negative infinity to t delta t dt. And this integral comes out to just be the unit step function ut. I'm not going to prove this integral because, again, this is just a simple example I want to get across to show you what I mean by this h of t being the impulse response of a system h. And again, we say that the impulse response in this case is simply this unit step function. And that's because my input was this delta t. In the upcoming videos, I will be doing examples of this to really clarify the point. But moving forward in this video, let's go ahead and note this definition. Again, that says that the impulse response h of t is the output when my system receives an input delta t. If you have any questions about this slide, please leave them down in the comment section below and I'll be sure to get back to you. Okay, to continue with our proof to eventually get the eigenfunction of a continuous time LTI system, which is the point of the video, we need to consider this theorem, which I will call theorem 1. And it says that an LTI system h with impulse response h of t is such that my output y of t, given any input x of t into my system, is equated to x of t convolved, or the convolution operator, with the impulse response. So that definition might be a bit confusing, but essentially it's saying that the output of an LTI system is given by the convolution of the input x of t and the impulse response h of t. So let's go ahead and prove this. And to prove this, we first say that imagine a system H that is a LTI system, which is both linear and time invariant. Using this assumption plus what's considered the convolution identity. And again, the convolution identity says that given any system x of t and you convolve it with this delta t, you're simply going to get back your original system. And this assumption, or this theorem, I proved in a previous video that I made called Continuous Time Fourier Transform of the Unit Impulse Function, clearly explained, and skip to minute 2, and you will find the proof of this convolution identity. But again, if we take this assumption where my system is an LTI system and the convolution identity, we can say that y of t is equated to my system when my input is x of t. Let me go ahead and use the convolution identity and say that we have a system, and we can say that my system can be the left-hand side of the convolution identity. So it's x of t convolved with delta t, or the Dirac delta function. And so in order to compute this here, we say that this is equated to my system h times the integral from negative infinity to infinity x of tau times delta t minus tau d tau. And so what we can do is we can pull this system into my integral here and have only the delta function be affected by the system. And so we have that this is equated to the integral from negative infinity to infinity x of tau, my system h, which is being affected by this delta t minus tau d tau. And now we can use that observation or definition from slide number 1 that says that if my input to my system is this unit impulse, we get what's called the impulse response. So then I can say that this is equated to the integral from negative infinity to infinity x of tau times this impulse response, or h t minus tau d tau. So now, just to write the entire output clearly so there's no ambiguity, I say that y of t is equated to my system when x of t, or an input, is passed through it, is equated to this integral from negative infinity to infinity x of tau h of t minus tau d tau. Whereas you can see this here is the convolution between x of t and h of t. So I can say then that this is equated to x of t, or my input, convolved with h of t, which proves my theorem number 1. And therefore, if you wanted to put this in words, we can say that we have shown that a function x of t passing through a system h with an impulse response h of t has an output y of t that is equated to the convolution between the input x of t and the impulse response h of t. And again, in the future videos, I will be doing an example to really drive home this point. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Okay, I've gone ahead and scrolled down to give myself a little bit more room because I want to talk a bit about this output y of t. As we can see here, this integral is very complex to solve. Specifically, every time we have an input x of t going through our system, or our LTI system, with an impulse response h, we don't want to be taking the integral every single time. So as engineers, we say that, is there a specific x of t that goes into my system or my LTI system that allows the computation to be algebraic or multiplication division? Specifically saying, is there a function where y of t, which is equated to my system when I input this x of t, where I can multiply it by lambda times my function x of t, right? And essentially, again, this is equated to this xt convolved with h of t. And if there exists a function x of t, that means that now I've gone from this complex solution, again, which is in calculus, to this more simpler solution, which is algebra. And as engineers, we like algebra over calculus. So this is the next step that we're going to take. And again, we say that this special function here, we're going to call an eigenfunction. And this special multiplier, lambda, we're going to call an eigenvalue. I've done a video in the past about eigenfunctions and eigenvalues, which I will post in the top right-hand side corner of this video. So please make sure to check that out to fully grasp what is going on in this section of the video. Again, if you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Okay, now from theorem number 1 and the observation we did earlier in this video, we can have or prove theorem number 2, which is the whole point of this video, eigenfunctions of a continuous time LTI system. So for theorem number 2, we say that for an arbitrary LTI system H with an impulse response ht and input function of the form xt is equals to est, where again this input xt is an arbitrary complex exponential. So again, xt is dependent on this independent variable t, and we say that s is an arbitrary complex constant. S is equals to a e to the j theta. Again, this is a constant. This is very, very important. So if our input function satisfies these two conditions, we say that the following holds. We say that y of t, which is x of t into my system H, is equated to, again, this convolution computation, which is also equals to h of s e s t, right? Where h of s is equals to the integral from negative infinity to infinity, h tau e to the negative s tau d tau. And what we want to note is that when you compute this, you do get some complex constant. Okay, that's very, very important that we understand that h of s is a complex constant or a constant in general. So given an output that is equated to hs e to the st here, we say that x of t, which is again this right here, is an eigenfunction of the system H with the corresponding eigenvalue h of s. I hope theorem 2 makes sense and it gives a leeway to what we're trying to prove. But in simple terms, we're basically saying that an LTI system H has an eigenfunction x of t is equals to e to the st and an eigenvalue h of s, which is equals to this function here. So let's go ahead now and prove this. So what I've done is I've rewritten our theorem number 2 here, and let's go ahead and prove this. So we say that, what do we know? We say that we know that y of t is equals to my system, where my input is some x of t. And since my system is an LTI system, we say that this is equated to x of t convolved with the impulse response h of t, or the impulse response of my system. Again, this was proven in theorem number 1. And so using the commutative property of convolution, we can flip the two. We can say that this is equals to h of t convolved with x of t. So we know that this computation is equated to the integral from negative infinity to infinity h of tau x of t minus tau d tau. If we go ahead and plug in, we know that x of t is said to be this e to the s t. So that means that x of t minus tau is equals to e to the s t minus tau. So then that means that this is equated to the integral from negative infinity to infinity, h of tau e to the s t minus tau d tau. Since this e to the st is simply a constant when we're talking about this d tau integral, we can pull it out. So we say that this is equated to e to the st integral minus infinity to infinity h of tau e to the minus s tau d tau. And again, keep in mind, if you compute this, you're going to get some complex constant or simply a constant. So we're going to say that then this is equated to e to the st times h of s. And if we flip this to make it satisfy this equation here, this is simply h of s times e to the st. And what we can say is that this is equated to h of s x of t. And that completes our proof. Something we should note is that this h of s is what we call the system function, or we also call this the transfer function. And similar to my past video, eigenfunctions and eigenvalues clearly explained, we talked about if we have a system h here and we want to find its eigenfunction, we need to find a function where if you multiply it by simply a complex constant by that input function, you're going to get the output y of t. And lastly, as we said multiple times, the reason why we care about these eigenvalues and eigenvectors is because this is algebra, right? You're simply multiplying your function x of t by this complex constant versus this here, this convolution is calculus, right? You're taking an integral. And as engineers, we don't want to take integrals or do calculus. We would rather map it to algebra and do our computations in the algebra domain, if you will. Okay, and if you have any questions or concerns on this slide, please make sure to leave them down in the comment section below, and I'll be sure to get back to you. Okay, before I end the video, what I want to do is I want to summarize the whole point of the video. And essentially, we say that to understand a LTI system H, we want to send our input x of t is equated to e to the st because we can simply multiply this input by our system slash transfer function h of s to get our output y of t. So again, this is a multiplication problem, which we prefer to do. Instead of there's a typo here, more tedious calculus computation with our input convolved with the impulse response h of t of our system h. Long story short, we would rather do this than do this. And this is the whole point of this video. Now in the next video, I'm going to do example of convolution. So my input times an impulse response. So that's going to be example 1, call it. And then in the next video, I'm going to do an example using h of s times x of t, or the transfer function times x of t. And this is going to be my example number 2. And in the third example, what I'm going to do is I'm actually going to take a circuit problem and correlate it all the way using convolution and eigenvalues and eigenfunctions to solve for y of t. All right, if you have any questions or concerns, again, please leave them down in the comment section below and I'll be sure to get back to you. If you liked the video, please give it a thumbs up and please share the video to your colleagues and friends so they can also obtain the knowledge given in the video. And lastly, if you like the content the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.